In this lecture, I will discuss about how much winding is protected by differential relay. So here a transformer of delta star has been shown. So if any earth fault occur in the star side of the transformer, so how much winding is protected by means of the differential relay, I will discuss in this video. So here a resistance is connected. The value of the resistance is such that the if any earth fault occur in the delta star side of the winding, this resistance will limit the fault current to the full load current. Okay, so the resistance is connected between neutral point and earth. So purpose of the resistance is to limit the earth fault current in the star side of the transformer to the full load current under its full capacity. So here the transformer turns ratio is such that V2 by V1 is equal to 1. Since the turns ratio is 1:1 and HV side or primary side is delta connected and LV side or secondary side is star connected, we can write that V2 by V1 is equal to 1 and per phase number of turn is equal to T2 in the HV side and per phase number of turn in the LV side or secondary side is T1. We can write that T2 is equal to root over of 3 to T1. Now any earth fault occur in the star side of the transformer at point that is the full winding capacity. Beyond the full winding capacity, the value of the resistance is such that it will limit the earth fault at full load current. So that is the full load current in the LV side is equal to V1 by root 3 into R, since V1 is the phase to phase voltage or line to line voltage. So phase to earth voltage is V1 by root 3, and since a resistance is connected in the LV side, neutral and earth, so full load current is V1 by root 3 into R. Okay. So now consider that earth fault occur at X percentage of the winding from neutral point. So what will be the voltage? The base to neutral voltage will be X percentage of V1 by root 3, and the fault current will be, that is IF is equal to X into V1 by root 3 into R, that is X into I full load current. So if any earth fault occur at X percentage of the winding from neutral point, the fault current will be X percentage of the full load current. Now since the fault current in the LV side or star side of the transformer is X percentage of full load current, so the primary reflection of the fault current will be, since the T2 by T1 is equal to root 3, so HV current, my primary current will be HV is equal to X by root over of 3 into X percentage of full load current. So the HV current is equal to X square by root 3 into IFL. Okay. So this is the primary reflection of the fault current if fault occur at a X percentage from the neutral point of the star side of the winding. And now in differential current, the differential current is the percent per unit current, that is the vector sum of the per unit current of the HV side and LV side. Okay. So if I divided this HV current by full load current, that will be the percentage of the full load current, or that is the per unit current of the HV side current in the differential relay input. So consider that it is a single end fed fault current, that is the fault occur during charging of the transformer, and the transformer is charging from the HV side and there is no fault fed from the secondary side of the transformer. So the IHV, that is the primary current reflection of the fault current, that is IHV is X square by root over of 3 per unit at fault occur at X percentage of the winding in the star side of the transformer from the neutral point. Now as per the differential characteristics, the initial setting is given, that is I differential greater than, which is normally given as 0.2 per unit. Okay. So this current, fault current must be greater than zero point 0.2 per unit, so that relay will send a trip signal to the circuit breaker. So in this case, excess coil by root over of 3 must be greater than zero point 0.2. So the I differential current must be greater than zero point 0.2 per unit in order to relay to sense this fault. So x square by root 3 greater than zero point 0.2 per unit. So by solving this equation, we can get the value of the x. That is the percentage of the winding at which fault is occur from the neutral point. That is x is equal to 0.59 or 59%. So if a fault occur at 59% of the winding from the neutral point, then the value of the fault current will be such that the differential current in the relay will be zero point 0.2 per unit or uh, okay. So 59% of the winding will remain unprotected by the differential relay if the differential current setting, that is the initial differential current setting, is zero point 0.2 per unit. So how much winding in the star side is protected by the differential relay is depend on the initial setting of the differential relay, that is I dip greater than. So I dip greater than is zero point 0.2 per unit, then only 41% of the star winding is protected by the differential relay if it is a single end fault, that is fault current is fed only by the HV side or primary side. So that is why the restricted earth fault relay is very much important for the protection of the protection of the transformer, star side of the transformer.